Okay, we're here in the new Otani Hotel in Tokyo, Japan. It's June 23rd, 2016. I'm Doug Fairbairn, and I'm here to interview uh, Shozo Saito. Welcome, and delighted to have you here. Thank you for joining us.
Thank you very much for inviting me that.
Uh, as I said before, we'll concentrate most of the discussion on your technical career and the contributions and decisions made during that time. But we'd like to start way back in the beginning and understand a little bit about when and where you were born, what sort of family life you had, and how that might have influenced your decision to pursue a technical career. So if you would just start with a little introduction to when and where you were born and family life, I'd appreciate it.
Okay, and I was born in the Gifu Prefectures. That is the middle of to the Japan,
Mm-hmm.
and that time in the 1950.
Mm-hmm.
So then I grew up, and Gifu Prefectures is the almost 10 years, and after that I moved to Tokyo.
Mm-hmm.
And to junior high school and high school and the university is Tokyo. So I'm going to the Waseda University, and I'm going to the some applied physics, the some section. To that time, and I'm run to the physics. Then
Let me stop you before we get into university time. Were either of your parents technical, or did you do
okay.
some? Did you do any electronic experimentation or hobbies when you were younger?
Okay, that is to my father is truly different in the area. That is the my father is working in the some consultant of the some company.
Mm-hmm.
So that no technical area.
No, no influence. Do you have brothers and sisters?
Or single.
Just a single child.
Then that means the no relation in the technical areas. But I'm just considered to the universities is I'm going to the some physics areas.
Mm-hmm.
I like the physics areas, so that's why I decided to go to the physics.
Okay. So you entered the university Waseda. When did you enter? What year?
Okay, and it's correctly that is the 1969,
Mm-hmm.
but my high school is the connected is the university, the high school.
I see.
So that's why in the high school to move to just no examination.
I see. You just keep going. Huh?
Just the escalator is good.
Uh-huh.
Yeah. So that is during the high school times, very I'm interested in the some physics areas.
Mm-hmm.
So that I learned some physics.
Mm-hmm.
So then I'm going to the university also is the same areas.
Mm-hmm. Where is Waseda University? Is it in Tokyo area?
Tokyo areas.
Uh-huh.
Yeah.
And so then you graduated from there in 1973?
And just I'm wondering that if going to the some doctor course
Mm-hmm.
or some companies, then I finally decided to go to the some company.
Mm-hmm.
Then I selected the company in there. It's so many famous company there in the Tokyo areas. That is during that universities, the senior guy to the same applied physics course. The senior guys go to the Toshiba. So I asking that him that if I'm going to the doctor course or some company level and research and centers, which is better? Then his answer is clear that you should go the company. So that is so easily to be decided. Go to the company. Then I'm just asking that the company and some high class levels, and if to the some some researching. The area is the same in the to universities and go to the company. The same kind of development. If I can do that, and I will go and Toshiba. Then I checked the that company level, or what kind of
research
and that applied physics areas.
Right.
So Toshiba is the one of the best. So research and development centers, the big one. Yeah. So and they finally decided to go to the Toshiba research and development centers.
And so did you immediately start working on semiconductor technology?
Little different. So that's a strange thing. Yeah. First of all, they said, okay, and during the universities, I'm to research for the ferroelectrics materials areas. So ferroelectric is the some to electric company research and developed. And I'm asking that the ferroelectric is very important for the futures the electric company. That the basic technologies to develop it is important. Then there's somebody there already in the research. There, I want go to the that laboratories going in.
So you thought you wanted to go into ferroelectric?
Yeah. Then my image-wise, they are already committed that, but it's finally different. So then they are very close to areas, to the memory areas. That the semiconductor, truly semiconductor technologies, not DRAM. But they said this is the same technologies for the ferroelectrics. Oh, yeah, it's very interesting. So then I'm going to the that laboratories. Then that technologies is now we said is the MNOS.
MNOS.
Yes. So usually in the semiconductor and structure is MOS.
Yes.
Metal oxide semiconductors.
Right.
But that position is between metal and oxide is the nitride.
Right.
That non-volatile memory. That the initial non-volatile memory development in the Japan. So finally, I understand that's so great technologies. Then I developed for the MNOS devices in the Toshiba till almost 1975 or 6 time frames.
So you worked on that for 2 or 3 years?
Okay, and that time almost 6 or 7 years for the MNOS.
Oh.
I developed some MNOS devices. It is so many devices. Then we try to going to some expand for the market, but some problem that not so acceptable for the data non-volatile memory
Mm-hmm.
in the market.
What was the problem was it a technical problem or a application problem?
Application problem, mainly application problems.
Mm-hmm.
So during that time, in the other side, the DRAM,
Mm-hmm.
they are developed in the Toshiba. And at that time, it is 64K DRAM.
Mm-hmm.
It is magnitude is different now.
Mm-hmm.
64K DRAM. Then
That was in development at that time?
that time in the development, another groups.
Right, yes.
Then so that time so NEC or Hitachi is a big company
Mm-hmm.
that already developed for the 64K DRAM.
Mm-hmm.
But Toshiba is behind
Mm-hmm.
of the data technologies. So one of newspaper there, famous newspaper in Japan, said the Toshiba exit from to the DRAM market.
Oh.
Some news is going there, so we are very surprised that. Then that time, the top management decided to much more technologies developed inside Toshiba.
Mm-hmm.
Then there are many resources put in the other areas. So myself is the target to move to the MNOS to the DRAM.
So they wanted to move more resources into DRAM. They didn't really want to get out of the DRAM
Yes.
business. They wanted to
Much
put
more
resources
input
in
the resources.
and grow the business.
Yes.
Uh-huh.
Then I'm just started for the next generation. The 64K, next is the 256K DRAM.
Mm-hmm.
Then I'm just learned and starting. Then also moved to the R&D center to the some division laboratories.
Mm-hmm.
So I already changed that. The researcher to move engineer
Yeah.
that time.
And were
Already
you working,
gave up.
are you working on the device part of it, improving the device characteristics?
Okay, and that time also strange is I'm a physician that applied physics,
Mm-hmm.
but device developed or some material.
Mm-hmm.
But they are asking me that the circuit design to
Oh.
the DRAM
Mm-hmm.
or big change.
Mm-hmm.
But unfortunately, my boss or everybody go to through there. I couldn't say that. I'm stay here.
Mm-hmm.
Then I moved to the DRAM,
Mm-hmm.
the design groups. Then I'm just started for the 256K DRAM, where that is the nMOS, N-channel
Mhm.
MOS transistors,
Mhm.
and the 256K DRAM, and developed. Then I'm circuit designer, and also I'm interested for some marketing that.
Mm-hmm.
Then that time those kind of high densities DRAM to use the IBM, HP, and digital, so kind of big company.
Mm-hmm.
Then I'm going to that
You're going to those companies?
those company
Uh-huh.
for sales. I'm changed to the engineer to sales.
Right.
Then
But this is before the product was developed. You were going out and
just developed, but nobody used that.
Okay.
The Toshiba they already exist there. They are thinking.
mm-hmm.
Then return to the Toshiba, the new market. Then I'm going to the IBM, HP.
So you actually worked on the circuit design for the 256K.
Yes, just
And-
a main designer for the 256K.
Right.
and also I'm going to the marketing.
So did Toshiba come out with the 256K at about the same time as the other major manufacturers?
Okay, and that time, our competitors it's much more faster than to develop, and they are already selling that.
Uh-huh.
Then our positions may be 5 or 6 position
Mm-hmm.
to the some making samples.
Mm-hmm.
Then I said to IBM or HP people, and that they are coming for the purchasing guy. Then I developed for the 256K DRAM.
Mm-hmm.
That is a function is good.
Mm-hmm.
So please listen to my presentation. Then they are going to the US. Then the 2 or 3 guy, the purchasing guy is coming there. Then I developed for that kind of DRAM. And they said, okay. And that funny story is at that times, I'm give them and some presentation.
Mm-hmm.
But he bring to the cafeterias, the corner of cafeterias, the round table. You some presentation, give me that. I said,
Give you sample? You mean give them samples?
sample and some presentation at
Right.
first.
Right.
That only 3 people in the corner of the cafeterias and the big noise there about it eating lunch.
Right.
Then finally they said, "Oh, you are 5 or 6 positions. We don't need more.
Mm-hmm.
So if you want some testing, put on the sample there.
Mm-hmm.
Okay, there. Bye. that's it. Oh, Toshiba position is that. Then unfortunately, so that our 256K is not going to the majorities. But the small company,
Mm-hmm.
they are using our devices,
Mhm.
but not majority.
Not the bigger companies.
So I'm decided it's 256K. It's more need for Toshiba product.
Mm-hmm.
Then also our top management said we should move to the next generation,
Mm-hmm. 1 megabit.
1 megabit.
Mm-hmm.
But the problem is 1 megabit nMOS is already started. Other groups, different groups.
Mm-hmm.
Then our top management said your group, you're project managers.
Mm-hmm.
So different type of the 1 mega DRAM you should develop.
Because the other groups had already developed.
nMOS.
Uh-huh.
Then my target is moved to the CMOS.
I see.
Then
Was-
CMOS DRAM.
So were your competitors designing CMOS or
And only Hitachi is there.
only Hitachi?
But the other guys is nMOS.
Mm-hmm.
Then I decided to CMOS DRAM.
Mm-hmm.
Then there are also Toshiba one more static memory. One of static memory, CMOS static memory,
Mm-hmm.
they are developed. That famous one, but that technology level is too high.
Mm-hmm.
nMOS DRAM low. So combine that technologies. That one of solution that.
Mm-hmm.
Then I developed the CMOS DRAM.
So were you doing the circuit design then again for?
Yeah, circuit design and a total project manager of the 1 meg CMOS
Oh,
DRAM.
of the whole
All
thing.
things. And designer also in the technologies, everything.
But you were behind, right? I mean, they'd already developed the
nMOS ideas.
nMOS, so you had to work very quickly.
Yeah. So that I managed some people to the circuit design also, and device technologies, its process, and the combine. Then they are moving targeted inside of Toshiba. Warming NMOS DRAM people, almost a half year or 1 year delay behind that. So we are running that.
You were 6 to 12 months behind the nMOS version?
Then we developed for the CMOS and the nMOS at the same time. Then I present the ISSC,
Yes.
1985.
Right.
That this time almost 10 DRAM is the present, the 1 meg. They including Toshiba nMOS 1 meg DRAM, and also is a 1 meg CMOS DRAM.
Right.
Also, other company nMOS DRAM. The only Hitachi is the CMOS DRAM. But these technologies and also performance is the super technologies and also characteristics. So that time in the ISCC is booming that. The Toshiba 1 meg CMOS DRAM is the best one.
It was the fastest,
and the
lowest power,
and the new function there. So everything. So then I bring back and Tokyo, and also everybody to the to that develop parts going to the mass production. But only Toshiba CMOS DRAM is a success for the mass production. And the other time, everybody to some behind us.
So the other CMOS DRAMs were not successful, or none of you were ahead on from any other 1 meg.
Any other nMOS or the CMOS, they are behind.
They all had problems.
Then they are only Toshiba is going to the mass production of the ports.
So now you were in the lead.
Yes. Then I go to the US again. IBM HP people. That I'm present that.
Right.
Everybody listen to that. There, I have a sample. Strange things. I'm going that. Big conference room.
Not just a little table.
Not a little, almost 20 or 30 people to listen to me, my presentation.
Right.
Wow, big difference.
Right.
Why isn't that? So that's simple, that you were first.
Right. So back up, by this time, I guess maybe at the 64K level, the Japanese companies had established a leadership position
Yes.
in DRAM, right?
Yes. 64K. 16K is a US company. 64K is some middle. And 256K, some DRAM, Japanese DRAM makers. They 1 meg, almost Japanese.
Right. So was the reason for that because of the technical quality or bigger investment? What were the reasons that Japan was able to take the leadership position in DRAMs?
Maybe both. And at first, it's the technologies, CMOS technologies. That was one of the key technologies that the Japanese company, some moving that areas. And the second things is just time. Every semiconductor company invest for their factories. But Toshiba at first to start it for some invest for their clean rooms.
Mm-hmm.
So that the timing is good.
So they put more investment up earlier to get the
Earlier
volume.
for 1 meg,
Mm-hmm.
because Toshiba is almost tiny in the 256K,
Mm-hmm.
but new investment everything to 1 meg.
Mm-hmm.
But the other company, they have to also to produce for the 256K.
Right.
So that some behind.
Right.
So new equipment they install at first in the Toshiba factories.
Mm-hmm.
So that timing is second things, and
Mhm.
the technologies and the timing. And also third one is market.
Mm-hmm.
So that timing is the computer market in the growing too fast.
Mm-hmm.
So everybody need for the high densities memory. So main memory target in
Mhm.
every computer makers is looking for that
Mm-hmm.
in the high density DRAMs.
Mm-hmm.
So that's a good timing for the everything.
Right. And also the quality and the yields for the Japanese product was much better and
Yeah.
the price lower, right?
Yeah. So especially to the high-end computers need for some reliabilities
Mm-hmm.
and also the performance itself.
Mm-hmm.
So that the timing is everything's meet for that timing.
Mm-hmm. So you were able to take a leadership position in the 1 megabit DRAM, and that was, so you presented this paper in 1985. Did you also start delivering volume production in 1985?
1987 or something.
1987.
Yeah. Then there are maybe 1989 or 1990 time frames,
Mm-hmm.
and the total semiconductor market, the Japanese share of almost 50%.
Mm.
So that every to going up. But
Right.
Toshiba is a top. For
Mm-hmm.
Then the 1 meg DRAM top makers is ranking in the Toshiba.
Mm-hmm.
So 64K below that, and
Mhm.
going up to the number one position. Also for the company levels, and that profit is a huge profit there.
Mm-hmm.
That a record,
Mm-hmm.
because DRAM is always some prices going and they go down
Mhm.
and they change to the next generation.
Right.
But 1 meg case, the Toshiba still keep for some levels, so higher profit. So data image wise is something bad.
Mm-hmm.
So next generation is always keep to the top level. That is too difficult.
So did Toshiba maintain a leadership position at 4 meg and 16 meg?
Fortunately, no.
Mm-hmm. Hard to stay there.
And that Toshiba is top, and the second is maybe Hitachi or something. Some ranking change.
Mm-hmm. So did Toshiba It's okay. We don't.
Yeah.
But it sort of, once you had the leadership position for 1 megabit, then you had the problem of you had to maintain that, and so perhaps we're slower to make investment in the 4 megabit and 16 megabit.
Maybe I think that the 1 meg is a keep to production
Mm-hmm.
some quantities. Then the customers required some 1 meg DRAM in some quantity. Keep that.
Mm-hmm.
But the other our competitors already gave up for the 1 meg.
Mm-hmm.
Then they developed for 4 meg at first.
Right.
Before our
Like you did.
Yeah. That is the same strategy. That.
Yeah.
Then unfortunately, 6 years later, the Japanese competitors developed for the 4 meg.
Mm-hmm.
Then I also tried to if that 4 meg is not number 1, was we wanna skip to the 4 meg and going to the 16 meg.
Mm-hmm.
That we try that.
Right.
But
Try to skip the generation.
Skip the generation. But development wise, it's okay that. But
Mm-hmm.
the production level, not follow us. Or some main factories, they are keeping that 1 meg. Then the 2 generation skip is too difficult.
Too difficult. Right.
So that's why our DRAM position is going down.
So when did Samsung and the Koreans become a major supplier?
4 meg.
4 meg.
4 meg in the 16. 1 meg is slow that.
Mm-hmm.
But the 4 meg, our competitors, Japanese competitors, also Korean competitors, they are starting for the 4 meg and the 16 meg.
Mm-hmm. And was that largely because of their investment in fab capacity and?
Not only development, and
Mm-hmm.
also they invest for the huge investment to their factories.
Right, right. Did they get their design technology from Japan? How did they develop the technology to design 4 meg and 16 meg?
To the we call that dead copy. Dead copies means to LSI is so easy that some purchasing some market
Mm-hmm.
and open that chip
Right.
and
And you look, yeah.
Then to analysis in the circuit. Then same one they are developed. Then that technology is moved to the 4 meg, applied to 4 meg and the 16
Mm-hmm.
meg. So that's the usual case.
Mm-hmm.
Then I think they down to our 1 meg DRAM.
Mm-hmm.
Basically, it's the same circuit they are using that.
Mm-hmm. What production technology was required for the 16 megabit DRAM? What line width or minimum line width or was?
Oh, okay. Maybe 10 micron something. I don't know. Sorry that I'm
That's
not to
okay.
say. Yeah.
I was just curious. How long did Japan? What was the evolution of DRAM technology within Japan? How long did they keep going, and what is the current status of DRAMs in Toshiba today?
Okay, and just started the 1 meg in the 1985. Then mainly to the mass production in the 1990 time frames.
Mm-hmm.
Then finally, Toshiba quit the DRAM business of the 2001. Then that the 10 or 15 years, Japan some majority of the DRAM areas.
Mm-hmm.
Then Toshiba quit for the DRAM 201. After that, the Korean people that share the huge up.
Mm-hmm. What was the largest DRAM that Toshiba put in production? Was it 16 meg or?
4 meg, 16 meg, yeah.
Mm-hmm. That was the last generation.
Yeah. No. Okay, and 64 meg also Toshiba developed.
Okay, 64.
That time so DRAM to the mainly main users is moving from to the mainframe computer to PCs.
Mm-hmm.
So that time the function some changed.
Mm-hmm.
Then the 1 meg DRAM is the usual DRAM access schemes.
Mm-hmm.
But the 16 meg or 64 meg is level of the change to the we call the static current, the almost a static memory operation.
Mm-hmm.
Much more easier than the usual DRAM access.
Mm-hmm.
Then that 64 meg where we started that the static currents memory. That invented myself.
Oh.
So that technology, I have a patent.
You have a patent on it.
Yes,
Uh-huh.
that applied for the static columns memory.
Mm-hmm.
That is also Toshiba some first time to
Mhm.
the applied for the market. So that time is also some recover that.
Mm-hmm.
But that technologies is the static column more for usual for the PC company.
Mm-hmm.
They are strongly using that their static columns.
It was still DRAM technology, but it had internal refresh or something that it would act like static RAM?
Okay, and refresh is controlled by the control pin that is the usual DRAM.
Mm-hmm.
But static column in the internally to generate refresh,
Mm-hmm.
the almost static memory.
Right.
Then there are now current DRAM is everything is static columns. Then there are that a good invention that.
Mm-hmm.
That the first time the Toshiba is that technology that we can, but the technology wise is everybody can copy that.
Mm-hmm.
Then
So-
there are Korean people. They are also the static cloud. That's the only patent I have, but
Important one.
it's only patent. P is there. Back to the Toshiba, but the other things.
So, as you went to 16 and 64 meg, did you also, the configuration was more byte oriented, or were there multiple bits accessed at once?
Yes, and for the PC application, and that thing, the fast and I/O static
Mhm.
column type of things on the wide I/O type.
Mm-hmm.
So many variety that.
Mm-hmm.
They usually by 1 by 4, but that 64 meg, that variety that everybody that to start it for the variety of the DRAM.
Mm-hmm.
So it is too difficult to keep for the some volume. So Toshiba side it is too difficult to develop for many things.
I see. So there were many different varieties, and
Yeah.
each one didn't have enough volume. Is that right?
Yes. So
So-
that kind of and business model is
Mm-hmm.
Korean people is much more good.
Mm-hmm. So, when did Toshiba make a significant investment in Flash?
Okay, and to the just decide for 201 quit for the DRAM business.
Mm-hmm.
So that time in the Toshiba has for the big factories, many big factories,
Mm-hmm.
and that we just started for the DRAM production in the Oita prefectures, and
Mhm.
that time we already started for the Yokkaichi, the big factory.
Mm-hmm.
Then they quit for the DRAM, for the empty
Mm-hmm.
But the equipment there we have. So that time we change to the some equipment, but it almost is same equipment. Then we develop for the NAND Flash memory and to using for the old DRAM equipment. And also that time in the DRAM cases, we are going to the U.S. is the factories, Manassas or the close to the Washington, and we also started for the flash memory, U.S. factories, but that is quit for the DRAM business, and that factory to sell for the other company. Then their all equipment, flash memory equipment, moved to the Yokkaichi factories. Then there we started all the NAND flash memory in the Yokkaichi factory.
So you shut down the U.S. factory
Shut down.
and moved the equipment back to Japan.
Yeah. We sell for the Micron.
Oh, you sold it to Micron Technology? Okay. So in 2001, you started switching over from DRAM to NAND Flash.
Yes. Same factories.
And equipment.
Equipment.
Very important. So, and Toshiba is still a leader in NAND Flash now, is that correct?
Yes.
So you've had to continue to build additional factory capacity
Yes.
and newer technology or newer factories to handle that. Is all your production coming out of Japan, or are you building factories somewhere else?
Now in the front end, it only Japan. At back end to assemble that,
Right.
that they are foreign countries.
So tell me, get back to your own personal career. Where were you continuing to manage the DRAM business up through 2001? And how did your career go with the?
Okay, and so my career is some different. It just strange. Who started for the research and development, and then moved to the design for the memory, and I also moved to the marketing guys, technical marketing guy, because I'm very interested to the customers, going to customers and listen to their requirement, and to realize for our technologies. So then I to move to the technical marketing position. Then the 64 meg or 128 meg in the to go into the majority companies. That time it changed to the PCs. Then I selling that that DRAM, and also new type of memories. That time we call the video RAM. Video special video application is memory. That time some of the people that some graphic board they required some video RAM. That developed, and also that time Numbers is famous of the company.
Right.
That is the first company to use for the Numbers technologies for the DRAM. Toshiba is the first one. That new type of memory developed, and I to go to the customers, and we develop those kind of new memories.
Mm-hmm.
So that's a position to move.
So was that when you were in the United States?
Yeah, that time I was
Mm-hmm.
to go to the United States.
So you could help, you could meet with the customers and understand better what their unique requirements might be. And
Then there are, so, and, no. Before the 2001, going to the US, and then back to the US, and I'm to the some working that in the DRAM sell to another company business. Then I sell all the DRAM business. Then I stay in the some technology executive to the NAND Flash memory.
mm-hmm.
Then still that engineer at that time. But after
Still,
that,
you say still doing engineering?
he's still engineering. The technology executive is the top of the engineering.
Oh, I see.
Then after that, I changed a job to move to the management side.
Mm-hmm. And when was that? What year was that?
Memory divisions, total memory
Right.
divisions.
What year did you move from the technology, finally leave technology to get into the management? Is it?
Okay, sorry. 2016年6年かその前は
So in 2002, you were in memory technology executive.
Yeah.
And then in 2004, you became vice president, general manager of the memory division.
Yeah.
So that was a non-technical position,
No,
right?
technical position.
Right.
2004. Yeah.
Right. And then, so you were, at that point, you were managing all of the memory, NAND
All
Flash,
the memory.
DRAM, and Toshiba wasn't making pure static RAM anymore. This was
That time already gave up.
already given up, right? And then you managed all of the semiconductor. So most of the other Japanese companies did some merging and combination of companies, but not Toshiba in semiconductors. Is that right?
Yes. So that time, so other competitors, so semiconductor division to spin out.
Right.
And they merged.
Right.
But only Toshiba is a keep of the semiconductor business inside. So that reasons Toshiba is also our customers. So inside customers, it is a good position to learn how to use for the memory or some semiconductors. So inside, especially TV. So TV, that market inside of almost the semiconductor. So that time, Toshiba TV is much more high share that connect for the inside of company, or PCs, laptop or something that the Toshiba laptop is high share that. So that communication is much important to the outside company compared to the outside company.
Right.
So that is Toshiba keep to the only Toshiba keep to the semiconductor divisions inside company. So that's a good timing.
Right. So today the NAND Flash memory is by far the biggest piece of your semiconductor business. Is that correct?
Yes.
What are the other areas where Toshiba has a significant investment in semiconductors? What type of semiconductors are you continuing to build other than NAND Flash?
the flash memory is the high tech in the market, the investment. But still we have for the discrete power devices or LED devices, and also our system LSI is some analog type of things. That area is we have, but not huge investment. But there's still some keep to the some technology levels or some production levels. So that areas is still we are to input for the some investment.
So NAND Flash is by far the biggest piece then.
Almost 80% to 90% in the flash memory, but
Right.
Still we have in the other areas.
Right. And the flash memory, that business continues to grow rapidly, is that right?
Yeah. So now the smartphone it is some booming that, and not only U.S. It is China or some the other development countries, and they are starting for the huge memory for the smartphone. That market is big. The other things is the data centers.
Oh yeah.
Now it is some change to the hard disk drive to the flash memory SDD.
Right.
So that's a huge market now is growing. And also now little bit change to the things in the IoT. So their IoTs is to market is coming, and they have each module has or there some data. So that is a small data. That is so good for the flash memory application. So that area it now is growing that. So still storage area is a good market for us.
Do you see technologies coming along that would change that would displace the NAND, the flash? Is there anything coming along that would threaten that position?
Okay, and this is the very difficult to see in the future. But technology-wise, some to going to the some breakthrough. But some physical limitation is coming soon for the flash memory. Then, for example, now our device is 15 nanometers. But 10 nanometers something, it is too difficult for the physical dimensions. Then we are now going to the 3D, which is too deep for the trench, and each layers. And now our develop for the 64 layers, the memory, 3D.
64 layers.
64 layer chip. Cell in the dips, and also some limited for the that areas within 5 or 10 years. So we need for the another type of devices, memory devices, to have to develop. So we are now considering to that areas, but we don't know that which devices is coming up for replacement for the flash memory. But sometimes it's coming that the physical limitation that times.
So there's the physical challenge, but there's also the physical challenge. That is the money part of it, right?
Yeah.
How much does it cost to build a 15 nanometer fab for flash memory? What is the size of the investment?
That huge investment, yeah. especially, for example, and to lithography technologies, some limited. Then they are now we are using for the immersion to I-line steppers, immersion steppers.
Mm-hmm.
That are prices or the huge prices for compared to the usual one, but there are some limited for the physical dimension for the lithographies. So we are going to the next lithography, the EUV,
Mm-hmm.
extra ultraviolet
Right.
lithography.
Right.
But they're too expensive for the some exposures. So that pay off for the per chip. So usually bit cost go down
Mm-hmm.
to the small dimension. But if we are using the EUV lithography tools, almost twice or
Yeah. Twice the cost per bit.
yeah. So that is too difficult.
Right.
If we can do that, so break through the physical dimensions,
Mm-hmm.
but cost is not follow.
Mm-hmm.
Then we need for much more reasonable cost of the lithography technologies or technology, the other some etching technologies. So
Mhm.
we have to develop or new materials coming. So that same things for the not only memories, the logic also,
Right.
also same
Sure.
thing that some
Sure.
limited for the geometries.
Right.
But for the memory side, one of good news is we can change to the some material or device itself.
Mm-hmm.
But the logic guys are only to almost the same for the MOSFET.
Mm-hmm.
So that is different. So we are looking for that the new material, that areas, not flash memory, the other material,
I
something
see.
magnetic or some the other material.
Mm-hmm. So, what? So going forward, do you see the monetary, the investment, the cost being a bigger challenge than the technology, or is it sort of?
Yes. So much more need for the breakthrough technologies
Mm-hmm.
compared to the before that. So used to be we are going to the so to deduce for the geometry only
Mm-hmm.
depend on the lithographies. But now is a much more variety. We need for the much more solution.
Mm-hmm.
We need for the much more solution that except for
Less
the,
expensive solutions.
less expensive, of course. So that's a challenge for the that is something to the some good challenge for the worldwide
Mm-hmm.
the semiconductor industries.
Right.
So now is a booming with the China industries, but the other things is a much more challengeable that area.
Mm-hmm. Do you see any of? Are there breakthroughs that you can see that might come through, or is it you have no idea sort of how to get beyond the current economic bottleneck?
We have some idea that,
Mm-hmm.
but we don't know that that is a good solution or not.
Mm-hmm.
So we are now just investigate for the which technologies is some good breakthrough for the futures. So now is many ideas.
Mm-hmm. How many bits are the largest flash memory now?
One chip is the 256 kana giga. a 64 giga bit.
Bit, 64 gigabit.
And also we have the stack chip, 16 stack, little one package. 256 gigabyte, one chip.
And you can make that today. That's technology that you can make in volume today.
Yeah. So everybody uses that, yeah. So PC, the SSD now is
Yeah, the SSD. I need a bigger SSD in my computer.
To first, everybody enjoy that.
And your smartphone has 256 gigabyte in it also.
Yeah,
So
I don't want one chip.
just one chip. That's for those of us who remember the days of 1 kilobit
Yeah.
DRAM.
I'm just started for the I'm to just start for the 1973 Intel to announce for the 1K,
Yes.
124 bits.
Bit.
Bit. That's a truly different.
40 years later, we're it's an amazing technology. So, are you still involved on a regular basis with these kinds of decisions with Toshiba? Are you asked as an advisor, or what is your role today?
My role is now in the advisors, to direct.
No management, direct
no
management. Right.
No direct management, but advisors. But we are going. I'm going to the any places. It's a factory. I'm checked at to the advice, strong advice there.
So you're still actively involved with things that are going on.
Yeah, yeah.
You visit different factories and
Yes.
Review what's progress and problems, and make recommendations as to steps to take and so
Yeah.
forth.
So that's why I said the semiconductor company in the industry still going ahead, moving. And so that myself also, until to my die,
You keep moving, right?
keep moving. So that the Toshiba has, you may know that the Toshiba has some nuclear generators. We call the big electronics and semiconductor pores. This one in the whale to moving to the slow in the big ocean. The semiconductor, the tiny fish going around the small areas. So big fish in the inside of the Toshiba whale and that small fish.
Which one has more investment?
Small.
Small. More money going into small than going into big.
Small, yeah. But small one still around moving there. That's my life.
So is Toshiba also making investment in totally new areas, biology or any of those, or strictly electronics, or what about bioelectronics?
Bio is just too, and the healthcare type of things, or so many type of the. So used to be Toshiba is the only two categories. One is the electric generation or something, infrastructure, we call the infrastructures. Then the other is the devices, memory. that we need for the third one. So that area now we are considering to the which areas in the future and some areas.
Mm-hmm.
So bio is something or the other. So that's a new challenge there.
So are you actively involved in making some of those decisions?
No,
No.
but it suggests the advice.
Uh-huh.
So also I'm working now in the sub-government in the for 5 or 10 years later. What kind of in the society is coming
Mm-hmm.
for the in the Japan or the worldwide.
Mm-hmm.
So looking for that in the 10 years later, or the we call just 2030 type of things. What type of society is coming?
Mm-hmm.
That society need what kind of the service or some hardwares, softwares. So one of the solution is the semiconductor industry also some contribute for the some areas.
Mm-hmm.
That discussion in the some government side. So for example, US in the internet ITT,
IoT or ITT?
is a consortium for the ITT.
Okay.
Yeah. And also the German for the Society 14.0. No, Industry 14.0. That type of the some government style. Then now in the Japan, they started for the Society 5.0.
Mm-hmm.
So that a new society is coming. So it used to be our information society, but 5.0 is the new to smart society.
Right.
So we are looking for that time.
Mm-hmm.
So that a consortium, worldwide consortium is coming.
So do you travel to other countries and have discussions of this type also, or?
Yeah. So especially, so I'm working for the Italian GSN. I'm a board member of the Global Semiconductor Association, GSA.
Yes.
So that is the every time I visit to the US
Mm-hmm.
for the GSA board meeting.
Mm-hmm.
So they are also discussing that the future of the industries, how to move that the new industry.
Mm-hmm.
Not only we are looking for not only semiconductor areas, it's much more wider societies.
Many challenges, interesting opportunities.
Yes. So I'm a GSA board member who Japanese representative, also JSIA, Japanese Semiconductor Industry Association, and the chairman. So not only Toshiba and semiconductor industry, all in the semiconductor industries
Mm-hmm.
to the areas as I'm working that position. Still moving that.
Mm-hmm. So you're very busy. Keep moving.
Yeah, the worldwide visiting that. So then start for the research and development for the R&D centers, and going to engineers, and some marketing guy, and the management. Now it is some consulting for the worldwide. So that is my life.
Well, good. So the next time you come to Silicon Valley, you must come and visit us at the Computer History Museum. We also are not only looking at the past, but looking at the future, and we have a number of new things going on. So I think you would find it very interesting to see and hear what's developing there. So I strongly encourage you to come visit us.
Thank you very much.
The next time you
thank you very much.
next time you come to the United States.
Yeah.
Is there anything else that you would like to talk about or cover, or do you think we've sort of completed?
Nothing.
That's it.
I talked to a lot.
That's good. That's what we asked you to do. Thank you very much.
Thank you very much.